Evening, everybody. Welcome. Yes, we are doing continuation from last class. In fact, what we are doing today is nothing but proofs. We are going to do a whole bunch of proofs, and I actually happen to find these fun. That may say more about my personality than it does about the proofs, but these proofs are, they're challenging, and they're kind of like putting together a puzzle. You just have to remember the rules, and once you remember the rules, you come up with a strategy, and away you go. Now, I am going to be putting up my screen over there. You should be able to see my entire screen at this point. Should be covering most of your screen, really the entire pod. Okay, good. This is our first proof that I want to discuss today. We're going to be doing a whole bunch of these, and after we do this, hopefully you're all going to be prepared for assignment number 3, and maybe we'll do one or two of the assignment number 3 problems before we head out for today. If anybody has any questions, there are not very many of you here now, so please feel free to chime in if you do have any questions. Okay, so this is our first example over here. We are given BAC is congruent to DAE, which is this. Essentially, this is angle BAC, which is this whole angle. Let me put it in red over here. BAC is this whole angle, is congruent to DAE, which is this whole angle. These two angles are congruent to each other. AE is congruent to AC. This is congruent to this. And A is the midpoint of BD. And what we have to prove are these two triangles. Let me put them in gray in terms of the two triangles we're going to need all together. These are our two triangles that we're going to need to prove congruent. Okay, so how are we going to this is a relatively simple one, but let's talk it out. Anybody have a strategy over here in terms of how we're going to prove these? We know that A is the midpoint of BD, so we've got. What does that tell us? What does the fact that A is the midpoint of BD tell us about these two bottom segments? What does it tell us about AB and AD? Well, the answer is that it tells us that they're equal, or it tells us exactly. It splits them equally, which means it tells them that they're congruent. So it tells us that this is congruent to this. And once we do that, we're going to have a side and another side, and then we're going to see if we can get the angle in between them or some other side. Okay, so let's first establish the bottom, that one thing that we just said. We'll say AB is congruent to AD, and the reason over here is that a bisector sorry about the sloppiness over here, but splits a segment into two congruent parts. That's the bisector rule. You can abbreviate it as the bisector rule if you like, but that's fine. Okay, now we've got a side and another side. How are we going to prove congruence? Well, we can either get the third side, I don't really see any way to prove that, or we can get the angle in between them. And of course, can we get the angle in between them? The answer is yes. We have this whole side equaling this whole angle, equaling this whole angle, in other words, BAC equaling DAE. So all we really need is to get 1 and 3. So how would we go about doing that? Well, think about it. If you subtract 2 from each of them, if you subtract angle 2 from each of them, they still have to be equal, because angle 2 is equal to itself. So what I'm going to do is I'm going to say angle 2 is congruent to angle 2, and that, of course, is the reflexive. In a lot of these proofs, we're using the reflexive property. The reflexive property means that an angle or a side or pretty much anything is equal to itself. Once we have that, now can we say that angle 1 is equal to angle 3? Or congruent to angle 3? And the answer is yes, because we know that the entire angle and this entire angle, EAD, are congruent to each other. When we subtract 2 from each of them, by definition, we have to still have something equal. So I'm going to abbreviate as the subtraction rule. When you subtract the same quantity from 2 equal quantities, the remainder, of course, has to be equal. Once we have angle 1 and angle 3, now, can we prove congruence? The answer is yes. We've got a side, we've got an angle in the middle, and we've got another side. So now we can say triangle BEA is congruent to triangle DCA. And we'll say because side angle side is congruent to side angle side. Okay. Let's do one more triangle one, and then I want to get to using a quadrilateral one. Okay. Let's try this one. And again, I haven't done these before, so you might have to help me a little bit, but that's okay. All right. How about this? I'll make a line over here and bar over here. Okay, there we go. Let's make it a little thinner so it's a little easier to write. All right, and as usual, we're going to put a statements column. Okay, and a reasons column. And I know this is a pain in the neck to always have to do, but let's do it because it's, it's good habit. Let's write all the givens out. Let's say angle 4 is congruent to angle 6. It says that the measure angle 4 is equal to the measure angle 6, but that's the same thing as saying the two are congruent because it's the same angle. Angle 1 is equal to or congruent to angle 3, and angle 4 is congruent to angle 5. Okay, let's write these out. 4 and 6. Okay, this is congruent to that. 1 and 3. So this, I'm going to put 2 lines to indicate that they're equal to the other 2 lines. And 4 and 5 also. So this is also equal. I'll just put 1 tick because that's the same as 4. And of course it's equal to 6 also, right? Okay. Now they want us to prove, and I'll put it in red because that's what we're trying to do. We're trying to prove angle R and angle T. I wonder how we're going to do that. Well, how would we go about trying to prove that sort of congruence here? Anybody have any suggestions on how we would go about doing this? It's me. Let's think about it. Let's see if we can get any of the triangles. First of all, let me write. I'll just write one big given over here. That will apply to all 3 of these. Fine. Okay. So let's sit here and figure this out in terms of how we're going to prove R and T. Now, if we could get triangles, if we can get the triangles that they're in to be congruent to each other, we can get them through corresponding parts. Is there anything else that we can get them through? Well, let's think about what other things this might do. So what other things we might be able to prove? Now, angle 4 and 6 being equal means that PQR is an isosceles triangle. If the base angles are equal, then the sides are equal too. So that means this side is congruent to that side. We don't know if that'll help yet, but it might. Okay, let's see. What else can we do here? What else can we figure out? 3 and 4 being equal to each other? I'm Are there any quadrilaterals here that we can get? This is a tough one. How would we go about doing this? Well, okay, what about the same thing as we did on the last one? What about if we tried to get this angle and this angle? Again, I'm just thinking of what we can get just by looking at this. This and this, by virtue of the fact that 1 is equal to 3 and 2 is equal to itself. Let's see, what would that do? I think it's going to be the it looks to me like we're going to have to get the two triangles PQR and SQT. You could split it. You could do anything you like. The truth is, you can do anything you like in terms of a proof. But now that I look at it, those are the two triangles that I think are going to be the two triangles that we're going to have to get, just by virtue of the fact that those are the only two triangles that I see that could be congruent to each other. Let me fill them in. Let me fill in the triangles that I'm talking about. Okay. This. No, that's a quadrilateral. I'm sorry. So I'm talking about this triangle and the other triangle that I'm talking about is STQ. Right, ST or QST. Right, that's this one. And for just like we did last time for the section in the middle, I'll make it purple. Basically, these two triangles with with the purple section being kind of overlapping between the two. Now, can we prove that? Well, let's see. And let me undo all that stuff, because that'll just confuse people if I leave that in there. So let me undo all that filling in here. Okay. And let me get this tool back for a second. Okay. So we've got an angle that's equal, this purple angle and that purple angle. We've got a side. Notice this side is actually part of both triangles. It's part of this side corresponds to this side. So we've got a side, we've got an angle, and we should have another angle because we've got 5 and 4. 5 and 4 look like they're corresponding also. So you got to kind of envision them separated. You kind of have to envision them. You kind of have to take SQT out of the mix for a second over here and see, well, we've got this angle of SQT that corresponds to this angle of PQR. Then we've got this side of PQR corresponding to this side of QST. Then we've got angle 5, which is part of QST, and we've got angle 4, which is part of QPR. So we've really got an angle, side angle of each one. And then once you have that, then you can get angle T and angle R based on corresponding parts. This is a hard one, but let's write it out. Let's figure out how we would go about writing this out. Okay, so let's say, so first thing we got was the purple angles. The purple angles were angle PQR is congruent to angle SQT because the addition rule being that, well, actually, I'm sorry, I really shouldn't say that. That should be, let me write it over here, but I'm gonna bring it down a notch. I'm going to bring it down a notch and put it down here. What has to be above this? What step did I skip? Anybody know which step I skipped over here? What I skipped was angle 2 is equal to itself. Remember, I needed the fact that angle 2 is equal to angle 2, exactly. So I'm going to say before that, I'm going to say angle 2 equals angle 2, or is congruent to angle 2 because of the reflexive again. The reflexive is in virtually all of these proofs. Okay, so now we have the addition rule because angle 1 and 3 are equal to each other. Add them both to angle 2, and now angle 1 plus 2 is equal to angle 2 plus 3. So now we've got that one off of the addition rule. Now we can say that side PQ is congruent to segment QS, or side QS, and that's because the sides of an isosceles triangle that correspond to the equal angles are equal. In other words, the fact that PQS has two equal angles, that means it's an isosceles triangle. And the fact that it has two equal angles means that the sides that correspond to them are equal. The side that corresponds to 6 is equal to the side that corresponds to 4. And now we've got angle 4 to angle 5, which was already given. We have that already. So now we've got the whole triangles. Now we've got triangle SQT is congruent to triangle PQR because of angle side angle. And now we have angle T is congruent to angle R based on corresponding parts. Let's try one with quadrilaterals. Let's try one where we don't just have triangles. We have quadrilaterals also. All right. Okay, how about this one? This one look like fun also? Again, let's make our little grid over here. Fine. All right. All right, statements. Reason. And we've got a quadrilateral here. We've got that symbol, by the way, next to FSLH, that means parallelogram. A symbol that looks like a parallelogram means a parallelogram. FLSH, which is given. FS is perpendicular to LG, and FS is perpendicular to AH. And again, all those things are true because they're givens. All right. Now we have to prove the triangle LGS is congruent to triangle HAF. So let's fill in that triangle. LGS and HAF. That's these two triangles, the gray ones. Those are what we're going to have to get. What do we have? Well, okay, we've got these two right angles. We've got LGS and FAH as right angles. They're right triangles, that's right. But let's say that they're right angles, even though they're perpendicular, because that's what perpendicular means. So I'll say, first of all, angle LGS and angle SAH, let's say, are right angles. And the reason is because perpendicular lines, or segments, form right angles. Okay. We have the hypotenuses that are equal. Okay, yeah, that's true also. So let's figure this out. Okay, so you're getting ahead of me. I'm drawing. I'm still drawing it, but yeah, you're certainly looking at the way to solve this. That's true. Okay, so we've already got two angles. So how are we going to prove everything else? Well, okay. The first thing, as Devore says, we can get LS and FH right away, because opposite sides of a parallelogram are equal. So right away we'll say LS is congruent to FH because opposite sides of a parallelogram are congruent or equal either way. Okay, now we've got an angle of each triangle, because this angle and this angle are both right angles, and right angles are equal to each other. So let's write that actually. We don't have that quite yet, so we have to write that. So let's say angle LGS is congruent to angle FAH because right angles are congruent to each other. Now we've got a side and an angle. Now what do we need? Well, we either need an angle or we need another side. Now, I don't see a way to get the sides so quickly, but I do see a way to get one of the angles. I do see a way to get another angle. Anybody see another way to get an angle? Doesn't diagonal of a parallelogram divide into two congruent triangles? That is true. That is true, but how would that get us to two smaller triangles? That would get us LFS and HSF, and then you want to reduce it somehow to get the other ones. You might be able to do it that way. There might be a way to do it that way, but I see a simpler way. Then you have the height of the congruent triangle. Well, because the altitude of yeah, okay, that's true. In other words, you can get it as altitudes because GL is an altitude of SFL and AH is an altitude of SFH, and altitudes of congruent triangles are equal. Yeah, that's true. You can get it that way. But I see an even easier way. Right. Okay. How about this? How about this angle and this angle? What are those? First of all, do we know that SL and FH are parallel to each other? They are, right? Because they're opposite sides of a parallelogram. And if they're opposite sides of the parallelogram, so what's the relationship between the two angles I just marked? They're alternate interiors. Remember alternate interiors? Alternate interiors are if two parallel lines are cut by a transversal. If you have two parallel lines and they're cut by a transversal, so angle 1 equals angle 2 because they're alternate interiors. If this is parallel to this, then opposite sides of the transversal, they're alternate interior angles. So yeah, and then once we have that, now we've got two angles and a side, and two angles and a side is good enough. So how about we say LS is parallel to HF because opposite sides of a parallelogram are parallel. Okay. And then what have we got? Now we've got the two alternate interior angles. So for example, we could say angle SFH, not ES, is congruent to angle FSL. And again, because they are alternate interior angles. Okay, and then once we have that, well, now we've got two angles and a side. We've got the two little blue angles over here because they're both right angles. We've got this one and this one because they're alternate interiors, and we've got these two sides already. So now we can prove that LGS is congruent to triangle HAF because AAS is congruent to AAS. Thank you. Yeah, a little more practice, and we'll get even a little better at it. Okay, so we've got so this is one with a quadrilateral. Let's try another one. This other one is a cute one also. All right. Well, actually, that's pretty easy. Well, let's do it. Why not? Whoops. That didn't work. Okay. Okay. Let's do one more. All right. Given parallelogram ABCD, and let's move it a little further over. Okay. All right, let's just abbreviate it. Statements and reasons, fine. Okay. Given parallelogram ABCD is a parallelogram, so this kind of angled one is a parallelogram. CE is parallel to ED, and BF is parallel to EA. Prove that ECBF is a rectangle. Okay, no problem. That's what we're here. We're not here to get everything right. We're just here to learn. All right. So how would we go about doing this? I'm just thinking about how we would go about. Now, we've already got two angles. Remember, to prove a rectangle, what do you need to prove? You need to prove that all four angles are right angles. This actually looks like yeah, this looks like a relatively easy one, to be honest with you. I'm just thinking right away. Remember, to a rectangle, as long as you can prove four right angles, you've proven a rectangle right there. That's really all you need. So we have one right angle here. We have a second right angle here. And this one we can get as a right angle because it's an alternate interior with this. You know, this is a right angle here because it's perpendicular. CB has to be parallel to DA because they're opposite sides of a parallelogram. And so therefore, let's call it angle 4 over here, has to be equal to angle 3. And so if angle 4 is a right angle, then angle 3 is a right angle too. And once you have three right angles, then the fourth angle has to be right also. Remember, a quadrilateral's got 360 degrees. So if three of them have 90 each, that's 270. If you have 270, well then the remaining one has to be 360. So if they're all right angles, bang, you've got a rectangle right there. So this actually happens to be a very simple one. All right, there are probably other more complex ways you can do it. You can probably get it on corresponding parts. If you can probably prove this triangle and that triangle because you've got an altitude, which is one side, and you've got the angle, which is here, and you've got the sides of the parallelogram, which are here. So you've got you've got high leg, and then based on the high leg, which because they're both right triangles, then you can get corresponding parts. So you can probably do all of that. So you can do it the long way, but let's do it the short way. So let's do it the short way. We'll say parallelogram ABCD, and CE is perpendicular to EA, and BF is perpendicular to EA, and all because given. Okay. So then we're just going to say what the right angles are. So we'll say angle CED and angle BF. I'm sorry. Well, CED, and we also want to prove angle 2. Let's say CED. We also want 4. So let's do all three of them. Let's say CED, which we called angle 1, angle BFD, and angle BFA are right angles. And the reason is because the perpendicular lines make or meet at right angles. So we've got all three of these things, the ones we called 1, 2, and 4, we've got all of them as right angles. So now let's do 4 and 3 equal, so we'll say angle BFA, that's 4, is congruent to angle CBF because of alternate interiors. They're alternate interior angles. Based on that, now we know that angle B, or angle CBF, is a right angle because it's equal to a right angle. If it's equal to a right angle, obviously it itself has to be a right angle. Once we have that, then we can say right away that ECBF is a rectangle, and the reason we'll say it has 3 right angles. And of course, once you have 3 right angles, it's implied that it has to have a 4th right angle. All right, do we have any other good ones here? All right, let's try this one. Okay, this one I'm going to ask for your help even more. I've done enough of these. All right, let's make our little chart here. Okay, fine. All right. What do we got? Well, we have ABCD is a parallelogram because it's given. Angle 1 equals angle 2 is what we're looking for. Anybody have any strategy suggestions? Oh, this is also an easy one. Okay, go ahead. Oh, and actually, no, it's not as easy as I thought it was. Let's see, that's equal to that. Huh. Is that possible? No, no, no. One would be equal to one. You're talking about the exterior angle rule. The exterior angle rule. If I put a 3 here and a 4 here, then one would be equal to 3 plus 4 because it's an exterior angle. But two's in a different triangle. Two's not in the triangle that one is exterior to. So really, as far as I can tell, this is really just two alternate interior angles. So, for example, this we know is parallel to this, and this is parallel to that. So, well, let's figure this out. If this, what can we get once we have angle 2? What else do we know is equal to angle 2? Who can name me an angle that has to be equal to angle 2? Okay, ACB, that's right. Let's say we'll make that angle 3. And the reason why that has to be equal is because it's alternate interiors. These two, AD and BC, are parallel. So 2 and 3 are alternate interiors. Oh, I'm sorry. Oh, you're right. You're right. We're proving that angle 1 is greater than angle 2. Okay. Right, right. Okay. Well, same way, same way. So far, I think right. Okay. So we're proving that angle 1 is greater than angle 2. Fine. Okay. So what do we know about angle 1 based on alternate interiors? What is angle 1 alternate interior to? It's at DCB. It's this whole thing. Exactly. I'll mark it in green. Angle 1 has to be equal to this whole thing because they're alternate interiors. Now the parallel lines are CD and AB, and the transversal is CB, which means the things on the opposite side of the transversal are angle 1 and the big green angle. So if angle 1 has to equal angle 3 plus whatever this thing is over here, well, then obviously angle 1 has to be bigger than angle 3 by itself. And if it has to be bigger than angle 3 by itself, well, then it has to be bigger than angle 2 by itself because angle 2 and angle 3 are equal to each other. That's the strategy that I would use to solve this. So let's write this out quickly. So we'll say AD is parallel to BC, and, let's do the same thing, and CD is parallel to AB because opposite sides of a parallelogram are parallel. Okay. Now we can get angle 2 and angle 3. So we'll say angle 2. Let's call them angle 2 and angle 3. There's nothing wrong with doing that. As long as we name them, we can put them there. Angle 2 is equal to angle 3 because of alternate interiors. Okay. Now, as we discussed, angle 1 has to be equal to angle 3 plus, let's name this angle 4. Angle 4, also because of alternate interiors, okay. So, therefore, angle 1 has to be greater than angle 3 because angle 1 was equal to angle 3 plus angle 4. And, just as importantly, angle 4 is greater than 0. Angle 4 is not a 0-degree angle. It actually has some, in order for something to be an angle, it can't be no such thing as a 0-degree angle. So because angle 4 is greater than 0, angle 3 has to be, angle 1 has to be greater than angle 3 by itself. And so therefore, we can say angle 1 is greater than angle 2, really by something called the chain rule, which was, I'll just say, the chain rule. It was is greater than angle 3, and angle 3 is equal to angle 2 that we proved earlier. We proved that 2 and 3 are equal, and we proved that 1 is greater than 3, so therefore 1 has to be greater than 2 by definition. All right, what do you say we try one or two of the homeworks, the homework ones? Any particular homework one that anybody wanted me to go over? Yeah, we've got, I think, how many proofs are on the homework? We've got 6 proofs for you on the homework. I guess we can go over one or two of them should be all right. All right. Let's try number 4. How's that? Okay. All right, there we go. And let's start again with statements and reasons. Here's a pretty complicated figure here. ACDF, the big thing, the big shape, is a parallelogram. And AD and BE bisect each other. Prove that BC is equal to F, or is congruent to FE. So let's put in red what we need to prove. We need to prove this is congruent to that. What do we have? Well, it tells us that AD and BE bisect each other, which means this is equal to this. It also tells you that this is equal to this, because they do bisect each other. And so how are we going to prove the ends? Now, what I can tell you right off the bat is that we're probably going to need to prove it by corresponding parts or by subtraction. I'm just thinking right away. I can think of a simple way to do it by subtraction. There's probably also a way to do it by corresponding parts. Yeah, ED is parallel to AB. That's true, certainly. Okay, okay, we also have that ACDF is a parallelogram. Let me put them in different colors. ACDF, which means this is equal to this. Opposite sides over here are equal. And diagonals bisect each other. So the easiest way that well, yeah, I mean, we can prove that that ABED is a parallelogram. Because one of the ways to prove that something is a parallelogram is that that angles bisect each other. Once we prove that that this whole thing in the middle over here is a parallelogram, well then, notice once we prove that, let's fill in this whole thing in the middle. Once we prove that this whole thing is a parallelogram, now we can get this whole side and this whole side. Yikes. Excuse me. Okay. Right, so we can get this whole side and this whole side. And we've got these two sides over here. We can get AB is equal to ED because they're opposite sides of a parallelogram. Yeah, and once we have this whole side, FD, equal to AC, and then we have AB is equal to ED, so then we can get EF and BC by subtraction. Because you're subtracting two equal quantities, two things that are equal, and you subtract two other equal quantities, what you left over has to be equal. So that's the simplest way I can see to get it. Get the middle thing as being a parallelogram because diagonals bisect each other, and then use that to get AB and ED, the two orange things, and then use subtraction. Are there other ways to get it? Probably. But yeah, there are probably other ways to get it also. But let's do it that way. Why not? Okay. So first of all, parallelogram ACDF, and the reason is given, and AD and BE bisect each other, and that's given as well. And now we can get the two now we can, first of all, we can get the, because we get those two things that are equal to each other. You know, honestly, we don't even need to write that AG is equal to AD or that EG is equal to EB. Just by virtue of the fact that the diagonals bisect each other makes it a parallelogram. We can say ABDE is a parallelogram because if diagonals bisect each other, the quadrilateral is a parallelogram. That's one of the 5 hallmarks of the parallelogram. The others being opposite sides are equal, opposite angles are equal, opposite sides are parallel, and consecutive angles are supplementary. If you can prove any one of those things, you know that it's a parallelogram. Once we have that, now we have AB and ED. AB is congruent to ED because opposite sides of a parallelogram are congruent. Okay. And now we also have the big sides, FD and AC. So we'll say AC is congruent to FD. That's also a parallelogram. Same exact reason. Opposite sides of a parallelogram are congruent. It's a different parallelogram, but it still works. There are two parallelograms here. There's a smaller one that's in gray, and it's the bigger one that encompasses the entire shape. And so now, once you have the big ones, FD and AC, and the smaller ones, AB and ED, well, now you've got FE, which is the thing you were trying to prove, being congruent to BC because of the subtraction rule. Again, if you take two quantities that are equal and subtract two quantities from them that are equal to each other, then the remaining ones have to be equal. Again, it's really common sense. I'm just wondering if there was any other way we could get, if we didn't have this, if we didn't have these, was there a way we could get the edges congruent? We'd have this angle and this angle because they're opposite sides of a parallelogram. Right, and we'd be able to get this angle and this angle because they're opposite sides of a parallelogram. And then we could say that this angle here is supplementary to the orange one. And then we could say that this angle here was supplementary to this orange one. And then we can get the two light blue ones because they're supplementary to the same angle. If two angles are supplementary with the same angle, then they have to be equal to each other. Supplementary means they add up to 180. This and this add up to 180, and this add up to 180. So if this and this are equal, then this and this also have to be equal. And now we've got angle side angle. We've got, let's say, this one over here with this one. We've got this one over here with this one. And we've got this side for this one. We've got angle side. Angle side is good enough. That gives you the exterior two triangles, AFE and BCD. And then we can get FE and BC based on corresponding parts. All right. Let's try. You know what? Honestly, I think you can do the rest by yourself. There's really only 4 proofs left. So I know it's a couple of minutes early, but if anybody, maybe I'll throw it open to questions now and see if anybody has any questions. Otherwise, maybe we'll call it an evening and meet again on Monday.